Yes.
Yes, we want to welcome Teacher Pio. Thank you so much for joining. Kindly take over.
Okay, thank you. I was waiting for the closing, for the opening prayer, but I didn't hear, but no problem. I think we can kickstart. It is a privilege that we are meeting again today. I think we last met sometimes back for this kind of exercise. So it's a pleasure that I have been given this same opportunity to interact. Today we are looking at paper 1, pure mathematics, A-level. And as you know, paper 1 comprises of 16 questions, and each, like in section A, we have compulsory questions only, and the areas from where we can get these questions include, among others, we have vectors. From vectors, they usually set 2 questions. And from geometry, we also have two questions. Then algebra, we have 4. We always have 4 questions. Trigonometry, we have 2. And then analysis takes 6. And as you know, section A is compulsory, but section B, you have the opportunity to select from the given question, and you will always be requested to attempt 5. So that is the format for paper 1, A-level mathematics. And I want to say, when you look at the subjects we usually do at A-level, I believe mathematics is the easiest because it has only 2 papers. We have paper 1 and 2. Unlike other subjects like biology, chemistry, where you are expected to have 3 papers. So it makes it easy for us to balance mathematics, because with 2 papers, you can easily balance them and you get very good score. So that is a brief recap of what I can say. And I want to encourage my learners, my students. With mathematics, without practice, you don't go far, which means you should always practice. So I have a project with my student, and the project's name is Do 5 Today, which means every day you must be able to solve like 5 questions in pure mathematics alone, excluding paper 2. So if you also do the same in like paper 2, which means in a day you will be doing like 10 questions in mathematics. And when you do that for a long period of time, trust me, you are going to exhaust all areas in both paper 1 and 2, such that by the time you go to sit for your...
Are you sharing your screen?
Yes, please.
Are you sharing your screen?
Yes, can you? I am still sharing. I am just talking. I've not shared the presentation.
Okay.
Yeah. I'm going to, let me share the presentation. I'll try to share and see if we can. If it can be seen.
Not yet.
Not yet.
Okay, it is there now. It is loading.
There.
It's there.
Okay. All right, let me see. Is it clear? Some
clear,
response?
very clear. Very clear.
Okay. Thank you. So maybe to wind up my introduction, as As you have seen from the screen, that is my name, Samuel Opio. I am a teacher of mathematics and chemistry at Popo, the 6SS Anaka, and is in Waya district. I've been in service at least for a good number of years. It's almost coming to 15 years. So that is my brief introduction. Earlier on, we already shared the questions that we shall be discussing today. And in the process of the discussion, that's where we shall have a number of things, number of key points that we shall be noting. The question may look simple, but it's okay. They are just for purpose of presentation and to give some insights about what we can do in pure mathematics. So our first question is on polynomial, and in polynomials we have a number of key concepts that we can talk about. Can talk about the factor theorem, the remainder theorem, the factor theorem, polynomial with repeated factors, and so on. So basically, when you want to handle any form of polynomial, then you should know the standard form. And the standard form of a polynomial is given by our first bullet here, where we have let f of x be equal to g of x plus q of x plus r of x. Here, g of x is the divisor. You can also call it divider. Q of x is the quotient, and then r of x is the remainder. The remainder is also defined in terms of x, but in some cases you may find out that a constant. So when you look at our problem, we have a polynomial f of x is a multiple of x minus 3. Being a multiple means the polynomial is divisible by x minus 3 as the factor. And it has the remainder when divided by x plus 3 as being 12. We are now supposed to find the remainder when the polynomial is divided by x squared minus 9. So when you look at this problem, you realize that the polynomial was not given. And because of that, we need to write it in the standard form. And the standard form of the polynomial is where we have now f of x equals to g of x, q of x, plus the remainder, which now, this x squared minus 9 is our divider, be the divider, which is this. Meanwhile, the q of x is unknown, so you leave it as it is. Now, we define the remainder in terms of a function of x, and this is a polynomial of degree 1. So always the degree of the remainder, the polynomial, which is the remainder, must be lower than that of the divider or that of the polynomial itself. Now, it has been said up here that x minus 3 is a multiple of the polynomial here is a multiple of x minus 3. So when we divide by x minus 3, then we can equate this divider to 0 and we get x to be equal to 3. Then we find f of 3. Sorry for this was typing error. It's supposed to be small letter f. So f of 3, we substitute in this polynomial that we have written up here. Then we get f of 3 is equal to 3 squared, which is 9, minus 9. Then q of 3 plus 3x, 3a. Our x is 3, so 3a plus b equals to 0. This being a multiple, the polynomial being a multiple of x minus 3 means when you divide the polynomial by x minus 3, you get 0. That's how the 0 has come. And when we simplify this, we get 3a plus b equals to 0. And for that matter, we can name this as our first equation. The second part is saying when the polynomial is divided by x plus 3, the remainder is 12. So dividing by x plus 3, equating x plus 3 to 0, you get x equal to negative 3. So we now punch in x equal to negative 3 in the polynomial. Remember, I said this capital F is a typing error. It just jumped when I space. So for this case, we get negative 3a plus b equal to 12. These are two equations in two unknowns. With two unknowns, we can solve them by either elimination, substitution, graphical method, matrix method, any other method that is suitable. But remember here, you should choose one which is easier for you and the one that takes also less time. So I have decided to eliminate A. So when we eliminate A, we get B to be equal to 6. And then substituting for B in equation 1 or 2, you can put even in 2, you still get the same result. We find that our A is negative 2. And for this case, we put back in the remainder function. So R of x will be negative 2x plus 6. So that is for question 1. So for question 1, for the case of polynomial, maybe I will exit this. Probably I go to Smartboard and we see more. But if you have any concern, maybe I can take. If there's any concern about this topic, that is polynomials, it is welcome. Can I hear any concern or any question if it is there about polynomials?
I think no question at the moment.
Maybe we get that.
Okay. So since there is no question, probably we can move on then. So for question 2 is talking about vectors. Remember earlier on in my introduction, I said vectors will always have 2 questions and does not miss. You will not miss these questions on vectors. It will always be there. So it is also a good thing that you may have to do practice so that you get acquainted with the concepts of vectors. So for part A, we want to find the equation of a line passing through the point A, which is 1, 0, negative 3, and point B, which is negative 2, 4, 1. Now to get equation of a line, you need a vector which is parallel to the line. We call it directional vector. And you need a known point on the line. So when you look at this diagram, on this diagram, I hope you can hear me well. I hope I'm clear. So in this diagram, we can have the line. I have not shown B, the line AB. So we need a vector parallel to this line, and we call it directional vector. And our directional vector is given by A, which is equal to AB. I think B should be a point here. Let me show where B can be. on this. B can be a point here. So this is point B. Let me change the color so that you can see well. So point B is there. So our directional vector can be got by getting the vector AB. And vector AB is given by OB moving from O. You can move from A to O. That's why I have minus OA, because we are moving against the direction of OA. Then followed by vector OB. OB will be here. Sorry for. So OB will be vector moving from here to there. Now, when we put, they've given us the coordinates of point A, B. So from the coordinates, you translate the coordinates of point A and B into vectors. You can use the IJK notation, or you use the column vectors. You cannot as well use the column vectors. For example, A was the point given by -2, 1, 1, 0, and then -3. So this was point A. Sorry, this was point A. So the point A we translate to IJK component will give us this vector, and that will be the position vector of point A. Then for point B also, when you translate to vector notation, it will be -2i plus 4j plus k. Now, when you look at this one for point A, the j component is 0. That's why the j component has not appeared here. So when we get the difference, we get d to be -3i plus 4j plus k. Now, when you look at my presentation, this d is bold. But when you are using freehand, you cannot write bold letters. So you will write D, like this. Then below D, you put the vector sign. And when you're using this, it must move throughout your presentation, throughout your working. Students have the tendency of only, when they give in the paper, like in a printed paper, they make it a bold letter, meaning it is a vector. But when they're presenting on their work, they also write D as it is. And when you write just D as it is, it becomes a scalar quantity, which will not be right. So that is very important when you are dealing with vectors. Now, to get the equation of a line, you need a point. You need a point on the line. For example, we have point A with non-coordinates, and then the directional vector D, which we have already determined from up here. So you just substitute in. Now, when you want to move from O to R is now a general point, just anywhere on the line. OR is the same as moving from O to A, followed by A to R. But AR is some scalar constant. So here lambda, this lambda is called a scalar, or it is a constant. Scalar or a constant, that is R. That is lambda. Lambda is a constant. So when two vectors are parallel, you see AB, OAR, and D are parallel. Parallel vectors, when you have two parallel vectors, then one is a scalar multiple of the other. That's why we have now r equals to a which is the position vector of point A, and then lambda d, which is the directional vector. So when we punch in the values, I mean the vectors A and D, we get this, and this becomes the equation of the line. So this is already the equation of the line. So that is for part A. So when given any question on equation of a line, you must endeavor to find a point, a non-point on the line, and a directional vector, a vector which is parallel to the line. Then you come and substitute in this formula that we have put here. Then you get the equation of the line. So that is for part A. Maybe if there's any concern again on part A, if you have any concern on part A, please raise. If not, we can move forward. So we can move to part B1. Remember question B1 is saying the line intersects plane pi, whose equation is 2x plus 2y plus 5z equals to -8. This is the equation of the plane. We want to find the coordinates of point P. Now to get the coordinates of point P is on the plane, and at the same time P is on the line, which means its coordinate must satisfy the equation of the line as well as the equation of the plane. So here, what we do, we shall express the equation of the line parametrically. So from here, you let r, remember here the equation of the line was r equals to this. You let this r to be a general point. Let r to be general point x, y, z, so that the position vector of point r will be xi plus yj plus zk. So when we equate this to the equation of the line, we make x the subject. We collect the like terms on the right hand side. The I components are put together, and then the j components also put together, and then in that order. So we have x equals to 1, because in this one the coefficient of I is 1. Meanwhile, here the coefficient of I is -3 lambda. So x is 1 minus 3 lambda, y is 4 lambda. Here, in the first vector, there is no component of y or z, or j. So we only the component of j we have is going to be this 4 times the constant here. So we have 4 lambda. Meanwhile, z is -3. Z is -3. So for this case, you can see that we have z is equal to -3 plus 4. So substituting in the equation of the line, of the plane, we get the value of the constant lambda. So from there we can now determine the value of lambda, and the value of lambda, as you can see, let me delete this, it will interrupt with our presentation. So the value of lambda is 5 out of 22. Now we go and put this back here, where we have x defined in terms of lambda, y defined in terms of lambda, and also z defined in terms of lambda, and find the value of x, y, and z. By doing that, By doing that, we get x equals to 7 out of 22, y is a 10 out of 11, and z is negative 23 out of 22. Here you should write the simplest form of the fraction, as simple as possible. That's why you can see for this part, we have expressed as 10 out of 11. Now you write these values in coordinates form, and that will constitute the point of intersection of the line and the plane. So generally, when you want to find the point of intersection between a line and a plane, you must express the equation of the line parametrically. Sometimes the equation of the line may be given in this form. Maybe we first illustrate it a little bit. Let me try to illustrate this. It may be given as x maybe plus 3 over 2. This is 2 equals to maybe y minus 1 over 1, maybe negative 1 like this, equals to z out of divided by 4. So how do I express this in parametric form? Because if you want to find the point of intersection of this line and any other plane, you must first express this in parametric form. So for this case, you equate all this equation to some constant. Let me use this side. Maybe you equate it to constant lambda. Then you equate each part to lambda. You equate, for example, this one to lambda. Then this one also to lambda, z out of 4 to lambda. Then you will find the value, the expression of x, y, and z in terms of lambda. And that will be the parametric form of the line, which you can now go and substitute into the equation of the plane. Then you solve for the constant lambda. So that is for the point of intersection of a line and a plane. If there's still any constant there, please feel free. Let's try to be interactive. Anybody with some question before I move away? Okay. Now we go to part B. Remember, part B is asking us to get the angle between the line and the plane. Now, from the orientation of I hope the diagram is visible enough. We have the line L, which is this, then plane is there. From the line we have, then from the plane we can get the normal vector. From the plane we can get the normal vector, and the normal vector, when you have equation of the plane, the equation of the plane is 2x plus 2y plus 5z equals to -8. Now, the coefficients of x, the coefficient of y, and the coefficient of z, when you bring them together in vector form, will form the vector normal to the plane. So that's how we get the normal vector n. So this is the vector which is going to be normal to the plane, and this vector meets the directional vector which is parallel to the line. So if the angle between the plane and the line is theta, then we can get theta from the relationship theta equals to 90 degrees minus alpha, where alpha is the angle between the normal vector to the plane and the directional vector to the line. So that is how we can determine the angle between two vectors using the definition of dot product. And the definition of dot product is given as d dot vector d dot vector n equals to the magnitude of the d times the magnitude of n cos of the angle between the two vectors. So from here, we dot the two vectors, and when we dot them, we equate them to the magnitude, the product of the magnitude, and then the cos of the angle. Now, when you are dotting two vectors, you multiply the components, the I components with the I component. Like that's why we have here -3 times this 2 is the one giving us -6. Then 4 times 2 we get 8. Then 4 times 5 we get 20. So that's how we get the dot product. Then we determine the magnitude from this side. I've seen Musa, you can unmute and ask.
Yes, sir.
Yes.
Thank you, sir. But I've got there is where I failed to understand. On the equation of the plane, you have said that the equation of the plane.
Yes.
You take.
I think maybe network, you are not very clear, Musa. Maybe you speak again.
I beg your pardon. On the equation of the plane, I've not got.
Okay. Here the equation of the plane was given. We want to find the angle between the plane. We want to find the angle between the plane and the line. Now the equation of the plane, let me write again. It was 2x. So I'm using freehand, that's why it's not very clear, but I hope you can read. Plus 2y plus 5z equals to -8. This is the equation of the plane. From the equation of the plane, we want to get a vector which is normal to the plane. So the normal vector to the plane is simply got by extracting the coefficient of x. Here the coefficient of x is 2, coefficient of y, and the coefficient of z. So when you extract this, you write them in vector form. So we shall have 2i plus 2j plus 5k. I hope you can see it. So this constitute the coefficient of x, y, z constitute the components of the normal vector to the plane. And remember, I said if you are not comfortable with IJK notation, you can also write this in column form. I hope we have answered you, Musa.
Okay.
Otherwise, we can. Okay. Is it clear now?
Yeah.
Okay. Let's proceed. Okay. Thank you. Thank you, Musa.
You
Now,
too,
let's
thank you.
proceed. When we are getting, another thing is, there's always problem here when we are trying to get the modulus, which is called the magnitude. So when you are getting magnitude of a vector, for example, the first one here, this one here, you get the coefficients of IJK, square them and then sum them. That's why you have -3 squared. And always when it is negative, make sure you put inside the bracket. Make sure you put inside, because if not, you will fit in your calculator as -3, then you put squared outside. You squared on the 3, which means the negative has not been squared. So, and when you're also pressing in the calculator, make sure if it is a negative number, you put into bracket before you square it. This is a common mistake that students usually do. So we have -3 squared plus this 4 squared plus 4 squared. Then you do the same for this one. We shall have 2 squared plus 2 squared plus 5 squared. Then cos of the angle. Remember, angle alpha is the angle between the normal vector and the directional vector. So that is what we do. Then when we manipulate this, we get the angle alpha to be 79.14. Now this is rounded value. I've rounded off. But before you round off any value, make sure you copy what is in your computer display. You copy it first. Then you round to the appropriate number of decimal places. Now, the angle between the line and the plane is given by this. Theta equals to 90 degrees minus alpha. So we can now substitute 90 minus 79.14. We get 10.8. I mean 10.8 here will be the 10.86. Yes. Nansana? Nansana? Please unmute. Nansana? Have seen any concern? Hello? Hello? Wait. Hello? Okay. Oh, unmute. Kaliro High School, unmute. Hello? Kaliro? Kaliro High School, can you unmute? Hello? Can you hear me? Someone respond?
Hello.
Yes.
Hello.
Hello?
Yes, hello.
Hello? Yes, please, I can hear you.
Now, I was like saying, when you get.
Oh, sorry, your network. Maybe you repeat your concern. Kaliro, can you hear me? Hello? Okay. Let me. Hello? Sorry, we cannot hear you, Kaliro. Let me try another participant. Yes, hello? Onen? Unmute. Hello.
Sir,
Yes.
we would like to know whether you can share the work with us on PDF.
Whether we can share this work
The PDF.
on PDF.
Yes.
Okay, fine. After the presentation, I will do.
Thank you, sir.
Okay. Innocent. Okay, thank you, Innocent. Let me see. Mukanga, unmute.
Hello,
Mukanga.
everyone.
Hello.
Hello. Hello, everyone.
Hello. Yes.
Yeah, I would like to highlight Teacher Simon. Maybe what they have to know also is that if I'm looking for the angle between a plane and a plane, a line and a line, that's when I use the cos. But if I'm looking for the angle between a plane and a line, realize now there we shall use the sine. We shall use sine.
All right.
So if
Thank you.
Okay, so I get the coordinates of the normal of the plane. It's what I dot with a vector parallel to the plane. Then I equate to the magnitudes. Then I use sine theta. I think that method is the easiest. I can share the screen on what I have gotten.
Okay, fine. I have got you.
Okay.
What you are? Thank you so much. What you are saying is, you know, this cos of alpha is the same as sine of theta. Cos alpha equals to sine theta. So instead of using cos alpha, use sine theta, then you will straight away get the angle without going through getting the angle between the line and the normal. That will give you straight away the angle between the plane and the line. Thank you. Okay, Samsung, unmute.
Yes, good evening, sir.
Good evening. Unmute.
Like when you press, yes?
Yes.
When you press cos of the 22 out of square root of 41 times 40 square root of 33, it gives you 53 point something, but your alpha is something like 79.14.
Oh,
or maybe
let me confirm. Okay, because sometimes because of whatever type some errors, computational errors that can be, but let me confirm what you have said. So we have 22 divided by root of, we have square root of 41, then again square root of 33. So we get the cos of it. Okay, it is 53.27. Thank you so much. So,
yes, sir. Then another, I need some more light. For example, when do I first cross, I cross before getting the angle, getting the cross product.
when you I beg your pardon.
Like there is a scenario where you need to first of all cross before getting the angle, before getting the angle of the plane.
Okay. If you have been given points on the plane, assuming you have point A here, you have another point B and another point C. This is point A. Then we have point B and point C. And to get the vector normal to this plane, you first get the vector AB, get the vector AC. When you cross vector AB and vector AC, you get a vector which is normal to the plane. That's what happens. So,
Okay.
yeah, that's what you need to do in case they give points on the plane. So you have to get the vectors, then later you. So we make correction here. Actually in the PDF I'm going to share, we'll have corrected. So this is about this number. I think we can move forward to the next.
Okay, thank you, sir.
Okay, Nansana state, maybe Nansana, you can unmute. Nansana? Nansana? Hello? Okay, let me. Kalumba? Kalumba?
Hello.
Yes, Kalumba.
Hello. Hello, sir.
Yes.
We've used a different approach, but we're getting a different answer. We don't know what's wrong with yours.
We have corrected this. There was, error in the process of computing the angle.
Yeah.
There was error.
Okay.
This one should be the 3.27.
So we correct our answer to 2 decimal places only.
Yeah, for angles, you can correct to 2 decimal places, not more than that. Can be to 1 or 2. That is for angles.
Okay.
Okay, thank you, sir.
Did you get 53.27?
Pardon, sir?
What is the answer you got there?
The answer, the final one.
36.7.
The final one is 36.73 degrees.
Oh, after subtraction.
Yes.
Correct. Yeah, it's correct.
Okay.
Thank you.
Thank you.
Maybe I've seen another hand. Let me you allow me answer this first, then we proceed. Namanya, Ivan, unmute. Ivan, can you unmute? Oh, sorry, Ivan cannot unmute. Okay, maybe we proceed. We shall still have time to answer more questions, more queries. So we are moving to the next part. I think this is about the angle. Then we go to analysis now. Analysis, we have question 3. Question 3 is about this integration. We want to integrate part A, which is x squared plus 4 out of 3 plus 2x squared dx. Then this is part B. Let's start with part A. In part A, you should realize that in this technique, we have very many techniques in integration. One of them is function and its derivative. Like here, you look at whether you have a function and its derivative. For example, if we take the denominator here as the function and we differentiate, we shall get 2x. But the upper one is x plus 4. So for this case, you should realize that you need first to separate. So you split the numerators. So we shall have, when we split, we shall have x out of 3 plus 2x squared dx, then 4 out of 3 plus 2x squared dx. For this first part, now when I differentiate the numerator, when we differentiate the numerator now, we get, when you differentiate the numerator, the denominator rather, when you differentiate this with respect to x, we get 4x, but up here we have all the x, which means we have some missing term, and the missing term is 4. Now, what do we do? What we shall do at this point is to create the missing term. And since the missing term is 4, I can have 4 out of 4. So 4 out of 4 is the same as 1 out of 4 out. Then 4x will be inside. So that when I differentiate, this is exactly that. So it becomes natural log of 3 plus 2x squared. So that is for the first part. For the second part, we can see we can have this. Okay, let me try Citland, unmute and ask for what, give your concern. Citland. Sorry, okay. Yes, Nakayonji. Nakayonji.
Master,
Yes, please.
why I've not understood where you have brought the 4 in.
They are telling me that
I'm explaining. Maybe you listen to this again. Let me explain again. You see, after you have split, you see, we started by splitting the numerator. Now, when we split the numerator, we differentiate the denominator. If we differentiate the denominator, which is by the x of 3 plus 2x squared,
no, that one was the echo from where? It is the phone.
we get
The
4x.
phone is
Now, when you look at this, up, okay, here we have 4, we have x, here we also have x. But the 4 is missing, so you need to insert a 4. But inserting a 4, we are going to do a technique called do nothing. Do nothing, in this case, we multiply this by 1. And our 1 is written in the form of 4 out of 4. So that I can take this 4 up here inside. And when I take the 4 inside, I remain with 1 out of 4. 4 is here. So that now when I differentiate the denominator, I get exactly 4x, which is here. Then it means we shall have now, this is a constant, 1 over natural log of 3 plus 2x squared. So that's how we got the 4. Meanwhile, this 4 here is a constant we can pull out. That's why I have 4. Then we consider this, we now consider the integral of this. And for this case, we can let it to be equals to, now this is using the tan substitution. We can substitute, we change from x to u. Then when we do this, you make a the subject, find the value of a, then you make x the subject, then later differentiate the function with respect to x, or you differentiate what you have with respect to u. So we get the x equals to 1 out of root 2 sec squared u du. Having done this, we can go and substitute in the given function, which is given. So when we substitute, we get this. So we shall have 1 out of root 2 sec squared u, then over 3 sec squared u. So the sec will cancel. Then we have 1 over root 2. When we integrate, we get 1 over root 2 u plus c. Then when we substitute back for u, we get this. Then later you come and combine with the first part, and then we get the solution. So that's what we do. So that is, I'm seeing concern that I'm trying to answer them. Catalega Modern, can you unmute? Please. Hello?
Hello.
Yes? Yes.
Good evening, sir.
Good evening.
Good evening. I thought for the first integration, we are going to use changing of variables.
Yes. Okay. There are many techniques that may work still. This one here. We're talking about this, huh? Hello?
No, where we separated the integrals or integral
Oh,
of x, where we
this one.
separated integral.
Okay,
Yes,
this.
that one. Yes.
You can use change of variable using, you can use the same, right? Using the same variable here. It may work for all of them, right? What do you want to use? Maybe you tell us.
To let the denominator 3 plus 2x squared, to let it maybe to be u, and we differentiate.
Yes.
After differentiating, we are going to get the part of 4du, and we cancel
Yes.
the other x with the upper x.
Wow. Thank you. That is correct. So that is another way. That is correct. But this one also works. I hope you have got the same result. We shall see the final result. Let me hear from Sere, secondary school. Hello? Sere? Yes. Sere, secondary school, please. I'm not getting you. Okay, maybe we can proceed because I did not get that concern. So we go to, okay, maybe here we can, as he said, we can use substitution, because when you make this one to be another variable, say u, and you substitute and you differentiate, then later the x up here will cancel this, and from that you can find the integral as well. So that is for part A. Nakanyoni, please unmute.
Master, I'm not answering where root 3 has gone, because A has been root 3, but I'm not seeing root 3 now.
First, it is in the next slide, because at this point we have not substituted. You see? Oh, okay. The root 3. That is for A. Yes, the A here. This one, this root 3. A is root 3. But remember why it disappeared. Here we are letting it to be, look here. We are letting 3 plus 2x, 3 plus 2x squared to be equals to a squared times square u plus 1. Remember this, the one inside here is simply sec. This will be sec squared u. So a is this, but when you come back and substitute later, let's see, you come back and substitute later here in this integral, which is in the next page. We have this, it's going to be a squared. So the root 3 disappeared because we squared this part. I hope you are seeing. Let me highlight. The root 3 should have appeared here, but we are squaring it. That's why it has disappeared. Because this was set to be equal to a squared into tan squared u plus 1. So for that matter, the square root will disappear. So that is for that part. I'm seeing another hand. Please, Kabuda, can you unmute? Kabuda, unmute.
I guess you are getting me, sir.
Yes.
Now, when I look at that number, if we simplify it in that we pull out the 3, we are going to be left with 1 plus 2 over 3 x squared, is it?
Yes.
Then, if we don't want our learners to waste time on that number, we are going to have 3 into 1 plus 2 over 3, but everything under the root. Am I right?
Yes, you're right.
Then x, the whole thing is squared. No. Let me hope we are at the same page.
Yes.
Then if we just let tan of u as you used it as u equals to 2 over 3 x. Am I right?
Yes.
Because the 2 is having a root and the 3, is it?
Yeah.
Then from there, let us get the derivative.
Yes.
Then after the derivative, that we are going to simplify the problem very fast, I guess.
Okay, thank you, Kabuda.
Our learners will not complain too much.
Thank you. I hope they have also got, the idea. Okay. I have Madonna. Madonna, please unmute.
Yes, sir.
Yes.
Master, can you throw some highlights on where this square is coming from?
Where the?
The square on the tan inverse. Yeah.
Okay. Let me see. I think.
For us, here I'm getting
here
4 out of root 6. Tan inverse of root 2 x out of root
on the solution, eh?
B.
On the solution, this one. Is it this one?
Yeah. Getting 4 out of root 6. Tan inverse of root 2x
plus it
out of root 3.
What is the name of the formula?
Oh, this part, yeah. I've got the constant. I've got your constant. It's 4 out of root 6 because root 3 times root 2 should give us root 6, right? I've got your constant. And that is okay. Okay. I think I've answered. I've seen Unen again. Maybe as constant. Unen, unmute. Unen, unmute. Unen, unmute. Okay. Okay, let's proceed. We shall come back again. So we are going to the next part. Maybe part B. For part B, we are supposed to integrate from 1 to 2 the x over x squared into root of x minus 1. So one of the techniques we can apply here is change of variable still. So we are changing our variable from x to u. From x to u, so we are using the change of variable x equals to this one here. Then when we differentiate, we get the x equals to 2 sec squared u tan u du. Now, once you change variable for where there are limits of integration, like this case, you also need to change the limits. So you change the variables as well as the limit. That's why at the side in red, you can see, if you make u the subject from here, make u the subject. Remember, sec is 1 over cos. So u become cos inverse of square root of 1 over x. So when x equals to 1, this one here, when x equal to 1, we put 1 here, we get u equals to cos inverse of 1, which is going to be equal to 0. When x equals to 2, we get cos inverse of 1 over 2. That gives us the angle 45 degrees. The angle 45 degrees. But when we are doing integration and differentiation, your unit must be in radians. That's why to convert from here, 180 degrees equals to pi radians. So if I have 45 degrees, it will be 45 over 180 pi. So this simplifies to pi out of 4. So it is always a big concern that when you have this, you must make sure you change the limits. So that is the key idea in this case. However, some students first work out until the final answer, then later they bring the limits. But it's advisable to do it this way. It's going to take you a shorter time. So when we make the substitution and we put here, sec squared will cancel with a, because we have this. Let me illustrate just a minute. Now if we have sec squared here, u, and also here we have sec to the power 4, it reduces to sec squared down here, and tan u remain up. This thing inside the square root is simply tan squared u. So when you get the square root of tan squared, you get tan. The tan will cancel the upper one. So when they cancel, we only remain with the expression 2. Sorry. Let's go back up here. We remain with the expression 2 over sec squared u, which can be written as 2 cos squared u. So when we integrate this, remember we are dealing with the integration of even power of cosine. When you have even power of cosine or even power of sine, we use double angle formula or the double angle formula. And the double angle formula is, we know that cos of 2 theta equals to cos squared theta minus sine squared theta. So from here you can express any, you can express depending on the need. So using double angle, it simplifies to this. However, if you are using odd, if you have odd power of the function of cos and sine, you will use Pythagorean identities. So that is the difference between the two. So for this case, we integrate, then substitute for the limits. When you're substituting for the limits, you start with the upper limits. So we have pi out of 4 plus a half sine of 2u. We put 2u, we get pi out of 2 minus, then you open bracket, you put the lower limits, u is 0, so we put 0, a half sine of 0. So this reduces to pi out of 4 plus a half. So that is for part, for this part. So in a constant, I'm seeing some constants here. Let me start with it. Ibun. Ibun, unmute. Ibun. Unmute. Please. Ibun.
Thank you, sir. Now,
Yes.
our question
Yes.
was on the. Hello.
Hello, I can hear you.
You get us? Okay.
Yes.
Our question was on the slide, whereby you let square du. Now our concern, where do you get that?
This one.
Exactly there.
Yes,
sir.
Thank you. Now you need to use, because now we are looking for ways of simplifying this expression. We know from Pythagorean identities, we know that 1 plus tan squared u, is equal to sec squared. You get it? It's sec squared u. So from here, if you make tan squared u the subject, this one goes the other side. You get it? It will be sec squared u minus 1.
Yes.
Which is now similar to x minus. That's how it comes. So that you get, you know, where there is square root like this, you need to endeavor to remove the square root in order for you to integrate. So when you look at this, by letting x to be equal to this, you can easily determine the what? You can easily simplify that expression, and you will be able to integrate. So that is for how it came about. Let me see another concern. Another concern. Then Kamuse, Modern, can you please? Bishop, I'm coming to you.
Excuse me, sir.
Yes.
Excuse me, sir. In the question, we are given different limits. Then in our solutions, we have different limits.
Okay. What I was saying is, in this case, when you are, because we are solving this by change of variables, we are changing from, from x. Remember, we are integrating here with respect to x, which means this variable is in terms of x. But now we are using the change of variable from x to u, this one here. So for that matter, you also need to change the limits and we change the limits, you make u the subject from this substitution we are using. You make u the subject. And if we make u the subject, u will be this one here. Then when x is 1, you see 1 is here. You find the value of u, which is 0. When x is 2, you also find the value of u, which will be pi out of 4. So that's what happened when you're changing variable for where there are limits. Is it clear?
Master, let us have the table.
The table, yes?
Yes.
Yes, talk about the table. Do you have constant here on the table? Hello?
Yes.
Yes, what is the constant?
We are not understanding it.
Okay, what we are saying is, but is it okay for you here for the change of variable here?
For that case, we understood it.
Okay,
But
so
the
what we are
table,
saying, make u the subject. Remember, sec is 1 over cos. So we have x equal to 1 over cos squared. Cos squared u.
yes.
So when I multiply by cos squared u and divide by x, then I will have cos squared u equals to 1 over x. Then I take square root on both sides to get cos. So after getting cos u, which is going to be cos u, which is going to be equals to square root of 1 over x, I can get u, which is cos inverse of this one. Then I substitute for the value of x, which is 1 and 2, to get the value of u. But after, when you get cos inverse of 1 of square root of 1 over 2, you will get the angle 45. Then later you convert it to radians. That's how the pi out of 4 has come. So that is for the change of limits. Let me take another constant. You have got it now. Eh? Another constant, Bishop, please unmute. Bishop Rantino College. Can you unmute, please? Please unmute. Bishop? Okay.
Sir.
Yes.
So we are not trying to get what you're meaning by changing the variables to sec square. Why don't we
Yes.
sign substitution and we split the denominators?
We use? I beg your pardon. What do you plan to
I'm
use?
trying to say.
Yes.
I say, why are we choosing to use sec square in the substitution of x instead of using sign substitution?
No. Why we cannot use sign substitution? You know, that thing depends on how it comes. Maybe you will try and see if it works out. But I guess it will be very hard for you to get it when you make the sign substitution here. Because if you put x equal to, unless you are saying x equal to sign, but remember, sign, if you start with sign here, for it to be cos, it must be 1 minus sine squared. So you can say sine squared u minus 1 equals to cos squared. That's why it will not work out. Yes, teacher Simon,
Okay.
unmute. Teacher Simon, please unmute. Teacher Simon, please. Hello. Hello.
Hello, I think everyone's hearing me now.
Yes.
Okay, the number given there, in case someone can't use the trig, cannot use time substitution or sec, or they don't know trig, they can use another method.
Yes,
What
please.
you do, you equate the square root of x minus 1 to u.
Yes.
Maybe I can share the screen. I
Oh,
don't know if
wow.
I'm
Yes.
allowed.
Thank you. I've got you now.
Okay, so you
It
just,
works. Let me illustrate what as you talk.
I
So
think,
you're saying now we have square root of sorry.
okay,
You
so that is
share.
the
Very
screen.
good. Yes.
Hope everyone's seeing it. So that what you do, just equate that one to u, then you square both sides, you remain in the u squared equal to x minus 1, then after you differentiate. I'll get to u du equal into dx, then after I substitute now in the given question, where I see dx, I'll put there 2u du, then where I see x, I'll put x u squared minus 1, but because the x was squared, the bracket here is going to be squared. Like here I had x equal in 2. Now someone will wonder, how am I getting the u squared minus 1 and squared? What I did from this step here, I'm going to make x the subject.
Then you square it.
Yes, when I square, I'll come up with this one so people can continue from this step there.
Okay, thank you. Thank you, Teacher Simon.
You're welcome, sir.
Okay,
Yeah.
let me go back. Now we are, let me ask Mukora. Mukora, please unmute. Mukora.
Yes, sir.
Okay. Yes.
I'd also wanted to find out, can we use 1 plus cot squared equals cosec also to be applied there? Because
1 plus?
we take a substitution of u is equals cosec squared.
Okay. Yes, it can work. Of course, cosec and sec, they all work. So that one is fine.
Okay.
All right.
Instead of taking it, let u be cosec.
Okay. Let me ask Kabuda. Unmute.
Yes. No, officer.
Yes, sir.
I want to know the problem of using the trig function.
Yes.
So the best way to handle it is by using substitution of variables which they are used to. For example, when I have this function here, I can let it to be u equals to the root of x minus 1. Then when I square both sides, I'll be having u squared equals to x minus 1.
Yes.
Then I'll be having u squared plus 1 equals to x.
Yes. Okay. Okay, I think you can stop there. It's okay. Another teacher also did the same. We have already shared it. So thank you so much.
No,
This is very correct.
Minus, that was not okay, please. We don't need to mislead our learners, officer.
Okay, thank you. I've got
the mathematics, please.
Okay, fine, sir. Okay, next is okay. I think we have answered most of the concerns. Let's hear from Innocent. Innocent, unmute. Innocent. Innocent, unmute.
Sir.
Yes.
The other concept I think is more clear than this one because these things that are already done confuse us as we students.
Which one?
The already calculated work, I think it's somehow difficult for us to understand.
Okay, the one I presented.
Yeah.
But the other U substitution is okay for you, right?
Yeah, that one is somehow.
Wow, thank you. You know, there are many ways of handling problems. So you choose one which is appropriate. I'm really very glad for those who intervene. I mean, those who interjected and gave us alternatives. There are always many alternatives, so which we can explore.
Yes, sir.
Okay, thank you.
Welcome, sir. Thank you too.
Our Lady of Fatima, please unmute. Our Lady.
So we were asking for you to elaborate more on your method because we had a different approach.
Yes.
We want you to elaborate more on the method you used.
Okay, thank you. So in this method, remember the other one is okay too, but all the same, all of them are substitution because you are looking for ways, simple ways of making this function integrable.
Okay.
And that's why we can use various substitution, provided it can lead you to the solution. So in this case, I've decided to use the change of variable from using trigonometrical functions. Instead of, someone also commented that instead of using sec squared you can also use, you can use cosec squared u. So that one is all okay. But the idea is to make this square root sign, I mean to simplify what is inside the square root, or to simplify the whole function so that you can integrate. So please just feel free to use any appropriate substitution. Guys, this would be Guru Ami Secondary School, right? Unmute. GASS, please unmute. Yes?
So, sir.
Yes.
Where did you get the sec squared u?
Okay. Okay, our concern is, okay, the concern is here. I've seen many people have got concern here, how we got the sec squared u. Now the idea is, are we seeing this square root? You can use an appropriate substitution, but I'm also, I by instinct, I saw that we know that, let me bring the animation. Now, we know that 1, this is from Pythagorean theorem, 1 plus tan squared theta equals to sec squared theta. So if I make tan squared theta, I take this one the other side. So this side now becomes 1 minus, sec squared theta minus 1. And when I compare this with what is inside, when I compare this one now with what is inside the square root sign, it means this one. It means I can take my x to be this part here. That's how I decided to use this. But however, you have seen from the other discussion, there's a simpler substitution that you can make if you are not very comfortable with this type. Okay. Lastly, maybe before we go to the next question, I will ask Chibale High School, unmute.
This is Nabongo Derek from Kibale. I got pi over 4 plus a half using sec square, using the sec substitution.
Yes.
The answer is pi over 4 plus a half using sec substitution.
Yes. Thank you. Let's think what you have What you have said is in agreement with this one, right? It is this one, pi out of 4 plus a half, which is the solution. Okay, let us look at part C. Part C is integration of tan inverse of 2x dx. So you need also to observe this carefully and analyze what method can be applied. That's the method which may be suitable for it. For me, I have seen that one of the suitable methods for this is using integration by parts. Integration by parts is usually for where we have products of functions. Like here I have u, see this formula in red? We have u, then the v by the x, and it's given by uv minus v, minus v, this is supposed to be du, not, is du. V du by the x times the x. Now, there's a silent one here that is not seen. So this function is yet a product. There is a silent one which we are not seeing. One here, just before the tan inverse. See that one in red. So we can let that one, we can let u to be tan inverse of 2x. And immediately, when we differentiate this, first of all, you will get tan u equals to 2x. Then when you differentiate and simplify, you will get that du by the x equals to 2 over 1 plus 4x squared. Meanwhile, the v by the x is equal to 1, the silent ones that I've erased. So from here, you integrate v and you get x. V is got by integration. But in this case, you ignore the constant of integration. You only take the integrand, which is x. Then when we come and substitute in this integration by parts equation, we get the integral of tan inverse of 2x dx equals to, remember our v is now x, which is this. V is this, x, which is now this. And u is this, which is tan inverse of 2x, minus. So when we get this, we substitute for uv. U is this, v is that, minus. Now inside here, we shall have v, our v is x, times the u by the x, which is this, which gives us 2x over 1 plus 4x squared. Now from this point, you can see that the simplest way to do this is look at the denominator. The denominator, when you differentiate, you get 4x. But up here we have only 2x, which means there's some missing term. There's some missing term. I think I will make correction here. I have detected there's some correction. So when I differentiate this, I get 8x. So 8x, it means I have only 2 here, meaning there's some missing term, which is 4 up here. So that's why we can express this as 4 out of 4. So that when I multiply this 4 by this 2, I get 8. So outside we shall remain with a 1 out of 4. So when I differentiate this, I now get 8x. So this is natural log of 1 plus 4x squared. So this will be the solution to the problem. So that is for number 3. We can still take constant if there is. concerned on, because we are going to leave this part, we go to another area now. We are leaving integration. But what I want to say is, we have very many techniques that we can apply. I've not listed all of them. When it comes to integration, you choose accordingly. Let's hear from, unmute, please. Bishop.
Sir. Yes, sir. The denominator you get 4x, but it's 8x.
Yes. Okay, when you see,
It's
when
not,
you differentiate,
it's not 4, but it's 8.
when I differentiate this part, I will get 8x, right?
8x.
8x.
Okay. So out of the 8, which means I'm missing 4 times 2 here to make what? Make 8. You're seeing? So this 4 is going to be 4 out of 4. I don't know whether you're getting it. It's going to be 4 out of 4.
No.
Wait. I have 4 out of 4. So that if I take this 4 inside and multiply it by 2, I get 8. You have seen now? Have you seen? If I multiply this 4 by 2, I get 8. Such that now, after differentiating this, I get 8x. So it is 1 out of 4 natural log of this function. I hope it is clear now.
Okay. Thank you, sir. Yes.
You're welcome. Let me get this one. And then is innocent. Unmute. Innocent, unmute. Yes, innocent. Okay, let's go to Erusi. Erusi, you can unmute.
Okay, thank you, sir. Thank you for the good work. Now, I was thinking that also when you let that tan inverse of 2x to be u, so now you work it out in terms of tan u. No, you work I need in terms of u. It may still work out. I think that is up for another time. Those who may have to try it out.
We let u be equal to this.
Yes, the whole of it. So that now, yes, so that tan u is 2x, and then you get
Yes.
dx. It may also still come back to also integration by parts.
Okay, okay.
Try later. Thank you.
Thank you. Act, can you unmute? Act High School. Yes, Act High School, unmute.
Excuse me, sir.
Yes.
Excuse me, sir.
Yes, please.
Hello.
I'm hearing you.
How, pardon for moment, we have interpreted the 2x out of 1 plus 4x squared.
Pardon?
Pardon for
I've left it.
we have integrated 2x over 1 plus 4x squared.
Okay. Maybe we use substitution because detecting function and its derivative is kind of tricky as well. What you may do here, we are here. This is where the concern is. You let maybe u be equals to, this is now another approach, not the other one. You may get this one better. 4 x squared Now you are changing from x to, then you differentiate this, the u, differentiate this side, and also differentiate the other side, which will give us 8 x dx. Okay? Make the x the subject, then later you come and substitute here. This x will cancel the one here. You're seeing it? So by 2, 1, by 2, 4. That's how the 1 out of 4 will come. So this is using another approach. But ideally, what we have here is just function and its derivative. So you go straight away to natural logarithm. Maybe we have seen act again, maybe, but let's start with this. Unmute, answer. Answer, unmute. Answer, unmute.
Excuse me, sir.
Yes.
The issue is from after letting tan inverse of x to be u.
Yes.
So I just found that explanation from du x equals to 1 over 1 plus 2 x, all of it squared. So that's explanation there.
Okay, thank you. Let's go. I got your concern. It is like this. We have from here, we take tan on both sides, so we shall get tan u equals to 2x. Yes, are we seeing it?
Yes, sir.
Then differentiate this side, we are going to get sec squared.
Yes, sec squared u.
Equals to, okay, this side will be the u, sec squared u, the u equals to 2 the x. You get it? Now we know sec squared is equal to 1 plus tan squared. Have you seen it? Sec squared is 1 plus tan squared.
Tan squared, yes, sir.
But tan square of u is equal to, tan u equals to 2x, which means tan squared of u is 2x squared. You have seen this thing I put in the box.
Yes, sir.
That's what happens. That's how this thing has come this way. I think you have got it now.
Master, continue up to here, 2 over 1 plus 4x squared.
Okay. Now, after that, we have already substituted. Remember, here was sec squared u, but we have already substituted. Then you again differentiate the angle itself.
Oh.
You know, chain rule, using chain rule. Use chain rule to do the differentiation here. That's why we need to differentiate the angle as well. So when you differentiate the angle to this part here, you're seeing?
Yes, sir.
The angle is this part, you differentiate it. And if you differentiate, you get 2. That's why the 2 has come here. Then the lower one, when you expand, when you square 2, you get 4. Square x squared, square x, you get x squared. Are you clear now?
Excuse me, master.
Yes.
When I integrate 2, divide by 2x over.
Go on.
I'm integrating the angle.
No, differentiating.
Which is d into 2x over dx.
Yeah.
So I've integrated 1 plus 2x, but all of it into it's squared.
Now, here you're saying here we are still differentiating.
Master, I think, master,
Yes.
Master,
Yes,
I
please.
think we shall have 2 over 1 plus 4x.
2 over?
Okay,
No.
so I've got you.
You have got it now. Eh? It should be like
Yeah,
this
I've got
because
you.
we are squaring this bracket here.
I've got you, sir.
Okay, thank you. Now,
Thank you, sir.
let's hear from Ibun and Teacher Simon. Then we move to another lesson, another question. Ibun, unmute.
Okay, good evening to everyone.
Good evening.
Okay, now I think the idea behind that, you have a simple method called Liat, in case someone
Yes.
doesn't
Excuse me,
know. Yes, please. So we use Liat. It is logarithm, then the inverse, the algebraic, then the trig and the exponential. So the first one, the one that comes first. So let me first share the screen so that I can show you.
Yes, we'll share the screen.
Okay, like it is here. So now here is our questions like this. So I write something like Liat. After writing it, the L stands for log or natural log. The I is trig inverse. The A is algebraic. The T is trig, and E is exponential. So after I look out for what I have here, now here we have the trig inverse. So that one's coming first, so I need it to be U. Then the one that comes last, I introduce a 1, so we have a hidden 1 here. So that is 1 dx, that's why I equate that one to my dv. This side, you integrate, then here, you just differentiate, then you continue with the method you have there already.
Okay.
So if I have maybe x to the, e to the power 2x dx, there what I do, I have an exponential, maybe I have another trig. So the one that comes first, you differentiate it. The one that comes last, you just integrate.
Okay, thank you, Teacher Simon.
You're welcome, sir.
Yes.
Excuse me,
I
sir.
think we answered you, right? I want to go to Bishop.
I have a question.
Yes.
Sir.
Yes, please.
Why don't you use the other approach of the box?
No,
integration.
Okay, it works. It can work as well, right? So you just feel free to use an appropriate method. And it is good for your practice too.
You could use any method.
Good. You can still use another method.
Thank you.
Maybe okay, innocent. Yes. Let me go to unmute. Caltex, please unmute. Caltex. Okay. Let's look at the next number, probably. We are going to look at the next number. Okay, question 4. This is a proof. This is trigonometry. We want to prove this. We want to prove that 2 sine inverse of x plus cos inverse of x equals to sine inverse of square root of 1 minus x squared. So, and then the second part is this. So here we have that if we let A to be sine inverse of x and B to be cos inverse of x, then sine A equals to x. You take sine on both sides, you get sine A equals to x. Then cos of B equals to x also. But cos of A is, from the Pythagorean identities, cos squared A plus sine squared A equals to 1. So when we take sine squared A the other side and take square root, we get cos of A to be square root of this. But sine of A is x, so we can put here. inside we get 1 minus x, meaning sine b can be done the same way. We get 1 minus x, square root of 1 minus x squared too. So now 2 sine inverse of x plus cos inverse of x is 2a plus b. Now from this point, we can consider the expansion of sine of 2a plus b. Using compound angle formula, this will be sine 2a cos b, then plus sine b cos 2a. So sine 2a plus b becomes 2 sine a cos b. Then times cos a times cos b again. Then this one will be sine b into 1 minus sine square a. So when we substitute, you remember these values where we got them earlier on. We substitute. And when we substitute, there is a common factor of square root of 1 minus x squared. When we put it outside, then we simplify what remains inside the brackets. We shall get to this point. Then when you take sine inverse, you get 2a plus b equals to sine inverse of square root of 1 minus x squared. So that is for part 1 for the proof. If there's any concern, you can ask. But what I want to say is, with the trigonometrical functions, you cannot do without the identities. Where do you find the identities? They are in the mathematical log table books. Most of them are there. So during exams, in case you may not be able to remember them, please ask for the table. It is allowed that the tables can be used during examinations. So that is my advice. For any trigonometrical problem, please try to refer to the identities. We have very many of them. The first one is the one we call Pythagorean identities. Then most of the others are derived from there. So that is what we have as far as that number is concerned. If there's any question or concern on this, otherwise we can look at the next part. Okay. So for part B, we want to prove that sine 10 degrees minus sine 20 degrees, 2 sine 20 degrees plus sine of 30 degrees over this is equal to negative tan of 5 degrees. So here we can take sine the other side. You know, addition is commutative, so you can interchange the position. So that's why I've removed. That's why I am able to remove. To move this one from the end, and put it at the start here. Here. So when you do that, and you apply the factor theory, the factor formula for sine plus sine, and the factor formula is 2 sine cos. So that's why we have here 2 sine of 30 plus 10 over 2 cos of 30 minus 10 out of 2. Then this part is there. When we simplify this, and you also do the same down. So when we simplify, we get 2 sine 20 cos 10 minus 2 sine 20. Down here is the same. There is a common factor which we can pull out. When you pull out the common factor, which is 2 sine 20, and the 2 itself, they will cancel. So we remain with only this simple expression. Now using again the double angle formula, this for this part, we use the double angle formula. So when you do that, the 1 will cancel with this. Then this one also, when you open the brackets, will neutralize this one outside. So we remain with -2. That takes us to the next slide. We remain with a negative sign of 5. Of course, 10 divided by 2 is 5. Then cos of 5 degrees. But sine over cos is tan. That brings us the result. So that is for the numbers which were provided. The floor is open for any concern. Yes, I'm seeing 2 participants. Mukura, you can unmute. Okay, let me start with Erusi. Erusi, unmute. Hello.
Okay, sir.
Yes.
In the question, like having on the right hand side, you're having negative tan inverse of 5 degrees, but here it's just tan 5 degrees.
Really? Oh, are you sure? Maybe let me check. Then that could. Let me check. Probably. But I remember it should be that. Okay, let's revise the work. I think it should be negative. Maybe you will make that correction. It should be negative because look at, I hope you are seeing where my cursor is. Look at this part. Look at this part here. If the question is having only tan, then you change, it should be negative. Because it is from this part that the negative has to be generated. Okay, that is, let me, okay, that was Erusi. So I think maybe we move on to question number 5. Now in curve sketching, there are 4 basic things that you need to do. 4 main things that you will do. Only 4. If you can establish those 4, you will be able to sketch a curve. One, you find where, number 1, you find where the curve cut the axis, both x-axis and the y-axis. So cutting the axis, that's number 1. Sorry, not axis. Cutting the axis, that's number 1. Number 2, you look for turning points. Turning points. Number 3, we shall look at lines of asymptotes. I will explain that one later. And then number 4, you can look for the regions where the curve lies. That is when you have a quadratic curve like the one given here. So let's follow one by one and see what happens. We have cutting the axis. When y is 0, when y is equal to 0, definitely you put here 0, x will be equal to 1. That is the only value of x, because you will get square root of 0 is 0, then you make x the subject, we get 1. So it means the point 1, 0 is on the x-axis. But when you look at this function itself, y is not defined when x equal to 0. When x equal to 0, the function is not defined. So for that matter, because of here, the curve does not cut the y-axis. Then, when we come to turning point, we need to differentiate. When we differentiate this being a quotient, we need to apply the quotient rule. I've not written the quotient rule here, but that's what we have used here. So for the quotient rule, you differentiate the denominator, which is your v. You differentiate also u. You get the u by the x, the v by the x. Then we come and substitute. U, our u is this, times the v by the x, which is 2x minus 2. Then u, which is 1 minus x, then the whole thing squared, times the v by the x, which is also 2x minus 2. So here the u by the x and the v by the x are equal. So when you simplify this, you get the y by the x to be negative of open bracket 2x minus 2, then over the denominator square. But at turning point, the y by the x equal to 0. So when we equate this to 0, we get the values of x to be 1. But initially, we have already seen that when x is equal to 1, y is 0. So the 1, 0 is our turning point. But you need to investigate the nature. We can investigate the nature using this one. We call this one the gradient table. So our dy by the x is this. Our dy by the x is this one. We need to investigate the sign of the y by the x, left and right of 1. 1 is the x coordinate of the turning point. So we have 1. When you substitute for x equals to 1 here, you get 0. And when it is 0, it means the gradient is flat, parallel to the x-axis. That's why here is flat. Then on the left, you put any number left of 1, just any number of your choice, so long as it is left of 1. Say you have put 0. If we have put 0 here, we are going to have negative outside times negative 2. So the upper one will be positive. The lower one is always positive because of the square here. So it makes the whole of this positive. Here we are only interested in the sign, not the value of the function you get. So you only write the sign positive. Positive means the gradient slants like this. It is from left to right. Then this one, when on the other hand you get negative, the gradient is this way. And this shows that the point 1, 0 is a maximum. So when you are determining the nature of turning point, you must make sure you find it using the gradient function, or we can use second derivative. Second derivative means you have to differentiate this function again with respect to x. Then later, you can substitute. If you have used second derivative, when you substitute for x equal to 1 and you find that the value of second derivative at x equal to 1 is negative, then it will imply maximum. However, if it is positive, it will imply minimum. This is somehow confusing to students because with the second derivative, most students think when you get positive, then it is maximum. It's not true. It is the other way around. So that is using second derivative. But when you substitute again and get 0 using the second derivative, it means point of inflection. So that is how we can determine the nature of turning points. We have two methods, using the second derivative and using the gradient table. So we proceed to, after this, we go to asymptotes. To get vertical asymptotes, you must go back to the equation of the curve. The equation is here. Let me show you. So to get vertical asymptotes, you equate the denominator to 0. Equate denominator to 0. That's why I have x squared minus 2 x equal to 0. So from here we get x equal to 0 and x equal to 2. So that is for vertical asymptotes. And remember, a curve will never cut the vertical asymptote, never. But a curve may cut the horizontal asymptote. To get horizontal asymptote, you investigate where y goes when x tends to plus or minus infinity. So for this case, you have to first divide by the x to the highest power. So before you punch in any value, make sure you divide by x to the highest power. That's why my function has changed to 1 minus 2 over x, because x squared over x squared is 1. 2x over x squared is 2 over x. Then 1 over x squared, we have 1 over x squared. Then you do the same with the denominator. Now, when you put a big value of y, whether positive or negative, these other terms where there are x will disappear, will go to 0, even in the denominator. So it means y will tend to 1. So for that case, the line y equals to 1 is an asymptotic line. It's a line of asymptote. So that's how we determine asymptotes. Sometimes in the process of dividing, if, for example, you have the degree of the polynomial in the numerator greater than that of the numerator, then you are going to get some function of x or a constant. So in that case, you will get what we call slanting asymptote. Now, the next thing you need to find is the region where the curve lies. How do we get these intervals? To get these intervals, this is what we do. From the equation of the curve, maybe let me bring back the equation of the curve to this. I'll take it to that page here. Let me put it up here. Now, when we equate the numerator to 0, we get 1. Equate the numerator to 0, you get 1. So I have 1 here. When this is 1, 1. When you equate denominator to 0, I get 0. And also I get 2. So you divide this entire line into these intervals. So here we shall have x less than 0. Here we'll have x lying between 1 and 0. Here I have x lying between 1 and 2. This one. 1 and 2, this. Then I have x greater than 2, which is here. So this is how we get that. Then you pick any value less in this interval, x less than 0, and put here. This will always be positive because of the square. But if I pick -1 and put here, this will be negative. In between 0 and 1, x is positive. Between 1 and 2, x is also positive. Greater than 2, x is positive. Then you pick also another value and put here. Any value less than 0, when you put here, you get negative. Here also negative. Here still negative. Then here is positive. Then we have this one divided by the product of this. So positive over negative times negative, we get positive. You do the same for all of this. So this one down tells you where the curve lies. So that when you come to the plotting, now, let me clear this first. When you come to the plotting of the curve, we can translate that. So the line of asymptotes, we have x equal to 2, and lines of asymptotes are drawn using dotted lines, not full lines. Then here, also we have y equals to 1, another line of asymptote. When you look here, for x less than 0, the curve should be, the curve should lie on the positive part of the y-axis. That's why it is here. And here there is no turning point. You draw the curve such that there is no turning point in this region. Between 1 and 2, when you look here, the curve should be in the negative part of the, so the negative part of the x-axis, the y-axis, which is here. And it has a turning point at 1, 0, and the turning point is a maximum. So when you draw the curve, it should not cut this line of asymptote. So the curve will behave this way. Meanwhile, for x greater than 2, the curve is positive. So since the curve is positive, it will take in that shape. Then later you write the equation of the curve, y equals to this. So that is for curve sketching. So in summary, I said there are 4 things that you investigate. You have to investigate 1, where the curve cut the axis, turning points, line of asymptotes, and the regions where the curve lies. So that is for that number. Let's see a constant now. Let's start with bishops. Unmute. Please unmute.
Okay, sir, thank you. Sir, I'm like, to get the points in that critical table, the critical values, how will we determine it?
This table. Is it this table or this? So for this table, I said when you want to determine the interval, you first look at the equation of the curve. You equate the numerator to 0, find the value of x. There we get 1. Equate the denominator also to 0, we are going to get x equal to 0 and x equal to 2. Then you have to divide the entire line according to those values. We have 0, 1, and 2. That's how we generate these intervals. Then you find the sign of this for each part. Then later you have to, because we are dividing x minus 1 squared by the product of x and x minus 2. So we shall have positive over negative times negative. Of course, negative times negative is positive. So dividing this by this, we get positive. So you do for all this. Thank you. Now, let's hear from GASS. Unmute. Yes, Gulami School, unmute. Hello? Yes.
Teacher, what if we find a situation where the curve has to cut our the asymptote? How do we sketch it?
No. Listen, I said a curve will never cut the vertical asymptote. If you find that it is cutting, then you need to revise your work. But for the case of horizontal asymptote, sometimes the curve may cut. So that one you don't worry. If it cuts the horizontal asymptote, that is fine. But for vertical, it will never. Because look at this function. This function y equals to 1 minus x. I mean 1x minus 1 squared over x squared minus 2x. When the denominator is equal to 0, then this function is not defined. Not defined. So when you get that it cuts the horizontal asymptote, for example, y equals to 1, and at any point, just feel okay. it works, but not the vertical only. Thank you. Remember also x equal to, x equal to 0, which is the y-axis, is also line over asymptote. But this one already, for this one, it's already involved. So it remains the same. Okay, so that is for curve sketching. And finally, our discussion has taken long, but it was good because it was interactive. Let's look at number 6, which is this differential equation. This is also another common area that usually come differential equation. It will rarely miss. So if you prepare yourself well, be sure of getting your full marks, because this is one of the easiest topic too. So we look at differential equation. Solve the differential equation. That is for part A, and then part B. Part B. Yes, please.
Yes, may I request, because I'm seeing we are getting a bit late, may I ask that you summarize and maybe
Yes.
them as homework?
Okay, thank you. Just in 2 minutes, I'm finishing with this number. Because part A is simple. Part A is just first order separable. So you separate the variables and integrate. But what my concern is, the initial conditions were not given in the question. But if the initial conditions were provided, like in my working, you can see, we have the initial condition. The initial conditions will help you to find the constants. So for part A is just simply first order separable, or first order separating the variables. That one you can do from, for example, from this you separate y to y, x to x. Then for part B, this is where you need to formulate the differential equation. So when you look at this, Jadon walks towards school which is 1 kilometer apart, away from his home. Then the rate at which he walks is proportional to the distance he still has to cover. Okay. So here the distance x is the distance covered, meaning the distance he has to cover is 1000 minus x. Remember, they are given in kilometers, but here we have 2 units, so you need to change to be consistent. So for this case, y negative, as is moving from home towards school, he is reducing the distance from school to where he is. So this is decreasing. That's why the negative has come here. If it was continuously increasing, then the negative would not appear. So when you're talking about integration, differential equations, you should see scenarios whether it is going to be increased or decreased. For example, growth is increased, death is decreased. So when you're expressing the differential equation, it must have the negative for where there is decrease in quantity. So this is also first order separable that you can separate. Then using the initial conditions, you are able to find the constant C and constant K. So this is what I had prepared for you. We can proceed from this point. You have already seen, having expressed the differential equation, you are able to determine the solution. Thank you. That's what I have. Maybe 1 or 2 concerns before we can close this session. Thank you.
I think we can give a chance to Innocent.
Yes. Innocent?
Thank you, sir. The thing is about the number we did before, it's called sketching.
Yeah.
Let's first go back to curve sketching for the moment. Now we are confused there.
Yes.
We had been told that when the powers are the same, like the numerator and the denominator, we always find the point of our inflection, right? The slanting asymptote, and we use long division. Is it right, or it was just?
Okay, it's okay. You can use long division, but look at this function. When you divide, because the degree of numerator and denominator are the equals. So when you divide even by long division, you are going to get a constant. You get it? And that constant will be 1.
Yes.
So even when you do long division, you are going to get 1, which is a constant, y equals to 1. However, if it was x cubed over x squared, you are going to get maybe 2x minus 3, something like that. So that will give you the line y equals to 2x minus 3, which will be the slanting asymptote.
Okay. So we should always use long division when the numerator is greater than the denominator.
Yes.
Thank you, sir. Yeah. Thank you very much.
Okay. You're welcome. Any other concern anyway? Thank you, Innocent and the team.
Yeah, we appreciate.
Thank you. What I want to probably what I can add on, especially in paper 1,
yes.
If you have any concern, I've shared my number just below the question paper.
Yeah.
So in case you have any concern, you can just contact me anytime. I will be able to respond. Yes, then Charles, unmute. Please unmute. Then Charles, unmute. If not, let's try Chibale. Chibale has some concern.
Yeah. Excuse me, sir.
Yes.
Excuse me, sir.
Yes, please.
Sir, I wanted to know how you integrated the other differentiation equation. Integrating.
The differential equation.
Yes, that one. Number 1.
This one, part A.
A.
Okay, part A is the first order separable. You can separate y from x. Have you observed that?
A.
Okay. Now, when we separate, we shall have the y over square root of y. Okay?
Yes, sir.
Now for this part, let me show you. For this part, you can take y up, then it will be y to power negative half. Okay?
Yeah.
The rule of integration is increase the power by 1.
Divided by the new power.
Yes, then it gives us this. You have seen it? Then for this other part, you can now use substitution. But still, this is a simple thing inside. You can use substitution u to be equals to 1 x plus 1. Okay? You're following, eh? So here the u will be equal to the x. Which means this one will be written as the integral of u to power negative what? A half. Okay? Then the u. So when you integrate this one again, you get this part. You have seen it? Because after integrating and putting back, you come back to this. Is that clear? That's how. Unfortunately, I forgot in the process of typing the question, I did not include the initial conditions. The initial conditions are here. X equal to 3 when y equals to 9. So you can use this to get the constants.
Oh.
Yeah.
Okay, thank you, sir.
You're welcome. Maybe we hear from. Okay, I was seeing.
Yep.
Yes, please.
Yes.
Any other concern from anywhere?
Okay, I think the rest of the concerns, Teacher Pio, we shall be able to respond to them. Good enough, we are going to share with them the edited solutions, so they will be able to access them, but also we want to let them try out those numbers, and then they can share with us their solutions, but they can as well share with the teachers such that they can be able to do more practice. But like you said earlier on, that mathematics requires the practice, daily practice, something we must do on a daily basis. And more so now, like pure mathematics, it needs that daily practice, and one concept leads onto the other concept. So please, we must practice daily in order for us to be competent. But allow me to thank Teacher Samuel for the wonderful presentation you have been able to offer this evening. Thank you so much, Teacher Samuel. It has been a wonderful presentation, and I'm very sure everyone has really gained a lot from this presentation. Students that have tried out, I think you have been able to check out the mistakes that you have been able to make in the process of trying to answer. We shall have other sessions, but allow me to welcome Mr. Ronald. Mr. Ronald, are you in position to talk? Okay.
Yes, Mr. Kaziba.
Okay.
Though I'm on the road, but I want to. Can you hear me?
Yes, you are very clear.
Yes, please. We are getting you, Ronald.
Yes, I want to thank you, Teacher Samuel.
You're
all the way
welcome.
from what is the school name?
Popo the 6 SS Anaka Noya.
In Noya.
Yes.
Those who don't know where Noya is, you need to go to the map. And I'm so happy that I'm in the middle of Kampala and I'm listening into a lesson from Noya. And that tells me that we can close this learning gap through technology.
Sure.
I want to thank you, Teacher Samuel, for saving your time and giving it to us. And I would like to encourage all the teachers who are on the call to continue interacting with us. We want to create more teachers like Teacher Samuel, and let us come to this session to support each other so that the learners of this country can gain from the experiences you've gathered from your schools. We will continue. Of course, next week we'll have some, but we will do whatever it takes to make sure the candidates prepare well. And please, candidates, work very hard so that you excel at your subjects. And for us, we shall always be happy to hear the good results that come out. Thank you, Mr. Kaziba and your team, and let us continue this effort. Good evening, everyone.
Good evening. Okay.